having the degeneracy, the denominator in the second order correction. So that blows up. Huh? Okay, so that's one of the reasons. And now one of the main reasons, let's understand it from a schematic perspective. Okay. So let's say if you are having, you start with some system, okay, like this thing, S0 plus lambda hi. Okay. So when you turn on the perturbation lambda, okay, so let's take this lambda tends to 0, what will happen? So in the non-degenerate case, let's understand only the first non-degenerate case, okay? So you start with some state, okay? So let's say you start with some state, okay, let me take this as 0 and 1, so this is your lambda, and let's assume your state is here at energy, and you shift on this side. So let's take some state which is non-degenerate, clear? So what will happen when you take, okay, so when you vary this lambda, so it may either you will be having the lowering in the energy or you will be having the, okay, so let's take only the second order case, the energy will get lowered out, clear? So let's say this energy curve, it will go, let's say this is the energy curve up to this very point, clear? So now let's take the other way around. You take lambda tends to 0, what will happen? If I take lambda tends to 0, so when there is no perturbation, this perturbed state here, so you are having here, this is your perturbed state, okay, so let's call this as N0 and this is N. So this perturbed state will map back to the unperturbed state, clear? So it will move back to the unperturbed state. Okay, so now if I am having degeneracy kind of, okay, so let's assume there is degeneracy. Okay, so what I mean by that, so let's take let's consider two states which are degenerate. Let me take M0, these are unperturbed states, and M0, these two unperturbed states which are degenerate. It means your energy, it is same. Let's call that as E0, like this thing, okay? E0, clear? Yes. But if I take their linear combination as well, so I am taking these as degenerate states. Now if I take their linear combination as well, like this thing, so N0, let's say alpha plus beta M0, their linear combination, okay? So this is also degenerate with what? N0 and M0, it is having the same energy. You active H0 on this very state, so what you will get? You will get E0 back, okay? Clear? So that how many states you are having now total? 3 states. Okay, the linear combination one and the other 2 states. So you are having a manifold kind of thing, let's say. Okay. So let's assume you are having 3 states here which are degenerate in energy. Clear? Now apply the perturbation. So what will happen? The effect of the perturbation is to lift up the degeneracy or to remove the degeneracy. Clear? Okay. So what it means? So you will be having 3 states, let's say, coming out when you apply the perturbation. Clear? Yes, okay, so now the problem is here. Now let's move back. When I take lambda tends to 0, where I should land? I'm looking the perturbative effects on one of the states. Clear? So in this very manifold, I am having how many states? 3 states available. It can be a large number of states as well. Clear? But I am considering only the 3 states. When I take lambda tends to 0, where these perturbed cats will go? There is an ambiguity in which state they will get reduced to. Okay, so there is a, because this state, it has the parent state here. This state is also having the parent state, unperturbed state here. This state is also having the unperturbed state. But all these 3 are what? Degenerate. They are having the same energies. Clear? Got it? So that means there is some sort of ambiguity on which state these, okay, in the limit lambda tends to 0, these perturbed cats get mapped to. Clear? So for this matter, I require actually the perturbation theory which will handle such kind of situations. Clear? Got it? Okay, समझ में?
Yes, yes.
So have you got the idea what I have? So let's start then modifying our perturbation theory. Let's start with the two-level system. Clear? So let's take a two-level system. So I am taking twofold degeneracy. Okay. So what does that mean? I am considering two states having same energy. Let's take M naught and N naught to be degenerate, okay, unperturbed cats. Unperturbed states are cats. Okay, clear? And we assume them to be orthonormal, like this thing. M naught, N naught, it is equal to 0 for M naught. Clear? They are orthogonal to each other. Clear? So can you give me an example of this situation? Let's forget about two-state problem. Let's have, if you are having a degeneracy where you are having eigenstates are the orthogonal states. The simplest of example, your hydrogenator. Clear? Take 2s, 2px, 2py, 2pz. Is it? So all the four states are degenerate and they are orthogonal to each other, and then you can normalize these very states. Clear? So px is orthogonal with py, py is orthogonal with pz, and so on. Clear? Okay, so we assume these states to be normalized. Okay. So we have, okay, so let me consider. Okay, so let's write the energy corresponding to these states. So call these that energy to be E naught, okay? Okay, so therefore we are having this linear combination. So let's take this cat K naught alpha M naught plus beta M naught. Clear? Let's take this very cat. Okay, so this is also degenerate. So I am having H0 acting K naught, that is equal to E naught. Clear? Okay, so now let's apply the perturbation. So this all with, so H naught. Clear? So let's apply the perturbation. So we turn on the perturbation. Okay, so that means I am having my H is equal to the total Hamiltonian, that's simply equal to H0 plus lambda H1, and H1 is our perturbation. Okay, so explicit form here is not is immaterial here. We'll take them later on. We'll take the explicit example of the Stark effect. Clear? Okay, linear Stark effect. Okay, so how to do it? So we'll consider now the perturbed cat and expand that in terms of the lambda. Clear? The way we have done where? In the non-degenerate case. Clear? Okay. So let's assume our cat K. So if it acts on this H, okay, if H acts on K, you will get this E. Clear? Okay? E is a function of lambda and K is also the function of lambda. Okay? So now expand. So you have this H is equal to H0 plus lambda H1. Okay. So now expand this K in terms of as a power series of lambda. How to do that? So I will write directly. Okay. So shall I write? Okay. So you expand first this K in terms of, okay. So this is the unperturbed state plus first order correction. Let's write K1, then you are having second order correction, okay, and so on. And similarly, you are having this energy, okay. So you are having the unperturbed energy corresponding to this state K0. Then you are having the first order correction, then you are having second order correction, and so on. Clear? Okay, substitute it in this equation. Let's call this equation as first. Okay, so what is that? So H is your H0 plus lambda H1, okay, lambda H1, and then active K1, K, so what is that equal to? K0 plus, yes, K1 plus lambda square K2, okay, plus dash, so that's equal to, now your E0 plus lambda E1 plus lambda square E2 plus dash, acting on this K, so that's in as this extension K1 plus lambda square K2 plus dash. Okay, so now let's gather the orders of lambda, the terms. Okay, so let's take order of lambda 0, that means the 0th order correction. Okay, so you are having here H0 acting on this K0. Here you are having E0 equal acting, okay, E0. So you are having this very equation, K0 is equal to E0, K0. This is true. Okay, now let's take the order of lambda. We'll go up to the order of lambda. Okay, what is order of lambda equation? Okay, so you are having H1 acting on this K0. Okay, then you are having this H0 acting on K1. Clear? So H0 acting on K1, it's order lambda. So that's equal to E0 K1 plus E1, okay, K0. Clear? And so on. So this is the first order. We'll do only up to the first order correction. Let's call this as second. Okay, now if you see, this K0 is actually the linear superposition of these two states. Clear? Okay, so we'll call this K0 to be the, okay, quote unquote, good eigenstate or the good state vector. I will tell you later on what does that mean. Okay? Okay, so let's forget about the terminology for the time being. Okay? So let's take equation second. So let's take equation second. Sorry, this equation second. What I need to calculate? First order correction to the energy. Clear? Okay. So what I will do, I will multiply this equation second on left by m0. Clear? So the first thing. So let's take this operation m0 h1. Then you are having this k0. Clear? Plus m0. Okay. So these are two states. We are having two states at hand, m0 and n0. Okay, so we'll take the overlap of this very equation, equation 2, with this m0 and n0 separately. Clear? Okay. So you are having this e0, m0, k1 plus e1, m0 and k0. Okay. So let's work it out. What is our k0? So this k0 is alpha m0 plus beta m0. Clear? Got it? Okay, so any more problem? Okay, so okay, so here k0 is also alpha m0 plus beta m0. Okay. So now let's look at this very term. So you are having m0 overlap with m0. So m0 is normalized. Both m state and n vectors, these are what? Normalized vectors. So overlap of m0 with m0 is 1, and overlap of m0 with n0, that is 0, because we have considered them to be orthogonal states. Clear? So this very term will give you simply as, okay, E1 alpha. Clear? Got it? Okay. So now let's look at this very term. So H0, since H0 is a Hermitian operator, it will act on this side. So you'll get here, okay, what you'll get? E0. E0, and then you'll get back M0, okay, K1. Clear? So it is an energy eigenstate, so this will cancel with this very term. Okay, so this term and this term cancels. Clear? Okay, so now let's look at this very term. So it is H1, H1 will act on, so it will be something alpha, okay, M naught, H1, M naught, plus beta, okay, M naught, H1, N naught, okay, because we don't know what are the eigenstates of H1, huh? Okay, so N naught and M naught are only the eigenstates of H naught, clear? Okay, so that's equal to alpha E1. Okay, E1 is actually the first order correction, clear? Okay, so let's call this as equation third. Okay, so now let's take an overlap of this equation second with N naught. Okay, so I have taken first with the overlap with what? M naught. Now I will take the overlap of this very equation with what? N naught. Clear? Okay, so I am having now N naught, H1, K naught, plus N naught, H naught, K1, okay, so that's equal to E naught, N naught, K1, plus E1, N naught, okay. Okay, so what I will get from this very equation? So I will get simply alpha, N naught, H1, M naught, okay, plus beta, N naught, H1, N naught, clear? And now this term, so H naught will act on N naught, you will get E naught, then you are having N naught K1, so this term cancels with this term, okay? Now what about this thing? So you will get here N naught K naught, only the N naught will contribute, so it will be simply beta E1. So this is, okay? Everybody followed it? Any problem? Good. So now let's rewrite equation 3 and 4 in the following fashion. Okay, so I can write 3 and 4 this way. So let me write this as M naught, H1, M naught. How many states are available? 2 states, M naught and N naught, okay? So then you are having this M naught, H1, N naught, okay. N naught, I will write it as a matrix equation, okay? Like this. So you are having this alpha beta, this is equal to E1 alpha. Can I write it? Yes. Okay. So what we have figured out? We are having a matrix equation. Clear? Okay. So if I need to figure out what this E1, what I need to do? I need to diagonalize this very matrix, and this matrix we call it as a perturbation matrix, because it gives you the perturbation, okay, effects of the perturbation on different states. Clear? Okay. So if you okay, so let's call this matrix as Hij. Okay. So ultimately, what you need to do, in order to figure out the first order correction to the energy, you require to diagonalize this kind of matrix. Clear? So now let's generalize this a bit. If you are having 3 unperturbed states, what you will be having? So you will be having a 3 cross 3. Now if you are having a G-fold degeneracy, it will be a G cross G matrix. Clear? And the matrix elements will be simply, you start with from first state, okay, okay, like this thing, M naught, one state, then all the off diagonal terms. Clear? So it will be something like this way. So if you are having, let's say, G cross G matrix, so you are having, let's say you are having 1, 2, up to dash, up to G unperturbed states. So you will be having, let's say, 1, H1, 1, okay, then you are having 1, H1, 2, clear, dash, so on, and you fill up the elements of this very matrix. Clear? Okay. So what we are looking for? What is our question? What is okay? What is our question? To find. No. First we need to find what is the first order correction to the energy. Clear? To figure out the first order correction. So that is here E1, is it? Okay. So I need to diagonalize this very matrix. What does that mean? That means you need to adjust this alpha and beta. Okay? So how we diagonalize a given matrix? You should know that. How we do that? Okay, you form a characteristic equation. Okay, but in practical, in reality, in mathematical sense, how we do that? Okay, how we do that? So you, okay, diagonalization is a kind of, what kind of transformation it is? It's a linear transformation, is it? You start from one matrix and go to the another matrix, having only the diagonal entries. What is that transformation called? Let's say if you are having an orthogonal matrix, what is that transformation called? Similarity transformation, is it? Huh? Have you heard it? Okay. So you okay, so this is a kind of, okay. So let's say if you are having a matrix A, you choose, okay, in order to diagonalize this very matrix A, you make a transformation on this very matrix. Clear? How? Okay, so let's call you are having a transformation like this in OA, let me write some O inverse. Okay, so that gives you diagonal A. Clear? So this is a kind of transform, we call it as a similarity transformations. Okay, these transformations are from actually a set of similarity transformation. Okay, similarity transformation means you take one matrix to the another matrix, keeping the properties of matrix same. Okay, let's say if you are having, let's assume you are having a matrix, 2 by 2 matrix having trace is equal to 0. Clear? And you make a transformation on that very matrix to another matrix, keeping the trace same. Clear? So you are having the transformation which takes your initial matrix to the final matrix, you call that as a similarity transformation. Clear? Similarity transformation keeps the property of the matrix same. Clear? Okay, so how you know that? Okay, let's say if you are having a trace of this matrix something, so the trace of matrix will be here the same. Clear? Got it? All the properties of this matrix will be reflected in this very matrix. Clear? So this is the similarity transformation. Okay, it is something reorienting from the linear algebra perspective. It is simply reorienting your axes. Okay, let's say if you are rotating something, you choose some frame of reference and you align x-axis, y-axis and z-axis. Clear? So that is the diagonal form. Okay. Now how to choose these very matrices? These are from actually a set of linearly independent vectors. Clear? Which are actually the eigenvalues of, okay, which are actually the eigenvectors of this very equation. Let's say A, you choose some vectors V. Okay, let's call this as lambda. Okay, so these O's are constructed from where? The eigenvectors of this very equation. You are having the same kind of situation here. Okay, so in other words, we can say here these eigenvectors diagonalize A, because what you are ultimately getting a number here. Clear? So if you are having, let's say, many vectors here I. Okay, so it is simply the diagonal form. Clear? You are only getting the diagonal elements of this very matrix. Clear? So in other words, I can say these these vectors diagonalize A. Okay? So I can say then these vectors are some good vectors. Okay, so you can choose any arbitrary kind of vectors, but they will not diagonalize the matrix A. Clear? So let's say if you have, okay, so let's put it, okay, let's make it short. Suppose if you are having, I will give a matrix. Clear? Okay, and I want you to diagonalize it, form an eigenvalue equation. Okay, you can simply okay, the first way to do the usual procedure, diagonalize it, you make a characteristic equation, find the eigenvalues, is it? So this is the general procedure. But in reality, what is happening, you have to figure out this O matrix. Clear? Got it? And where from you construct it? You construct it from the eigenvectors of a given eigenvalue equation. Clear? So you figure out it from the eigenvalues of this matrix A, let's say, sorry, these eigenvectors, okay? And from these eigenvectors, you constructed this O. Got it? So this is the procedure of the diagonalization. Okay, similarly here, we are having this kind of objective. So in reality, I need to figure out actually what are the values of alpha and beta such that this matrix is diagonalized. Clear? So in other words, I can put this in the diagonal form and I will get the values of E1. Okay? समझ रहे हो? Then I can say the vectors, okay, which give you, okay, which diagonalize this very matrix, I call them as the good eigenstates or the good eigenkets. Okay, if you figured out the good eigenkets, it means when you turn off the perturbation, okay, in the lambda tends to 0, so those perturbed cats will reduce to these good eigenstates. Clear? Somehow? Okay. So let's do it. Okay. So we'll take an explicit example, then you'll understand it. Okay, so let's diagonalize it. Oh, diagonalize. Okay, so let's call this matrix as Hij. Okay, so what are the elements? So you can, okay, so let's write. So this is H11, this is H12, and this is 21, and this is 22. And by the way, you can diagonalize the Hermitian matrices. You can diagonalize various types. Okay, so when you diagonalize the Hermitian matrices, the those of matrices will be actually unitary operators. Clear? Unitary matrices. Okay, so you have U acting on this H, and U inverse will give the diagonal of H. Clear? Okay, so now look here. Is this the Hermitian kind of thing? Since this is a Hermitian element, this is also Hermitian. So its object is here. Okay? So because these two are Hermitian conjugate to each other. Clear? So what is your matrix? So you, okay, so diagonalization means you figure out now determinant of the characteristic equation. Okay? So it is something H11 minus E1. Okay, then you are having H12, H21, H22 minus E1. So that's equal to 0. So this is your characteristic equation. Okay, so now solve it. So you'll getting two values of E. So let me write those E plus minus. So that will be, okay, just take this thing minus this objective. Okay. Anybody? Can anyone tell me? So it is H11 plus H22 by 2 plus minus 1 by 2 root of H11 minus H22 whole square plus 4 mod of H12 square. Okay? So these are the eigenvalues. So now you have seen this is a very fundamental formula for the two-state problem. Clear? I mean the very general answer of the energy splitting of the two-level system. Clear? Got it? Any question? Huh? Huh? Okay. So now you want to know what are the good eigenstates? Is it? So that we have already divided. Okay, so this M naught and N naught are already the good eigenstates. We have started with the good eigenstates already, yeah? Okay? So okay, so let's look at the, I mean, let's look at the limiting case. Let's remove the degeneracy. Let's remove the degeneracy. Let's say, have you got it? Why they are the good eigenstates? Huh? Because that has already diagonalized it, is it? We started with what kind of states? Two states, M naught and N naught, okay? And those, you are having these two vectors, M naught and N naught, okay? Okay, so when you are having a 2 by 2 matrix, what is the dimensionality of the Hilbert space? It's 2 by, okay, it's a 2-dimensional Hilbert space. How many linearly independent vectors are there? 2, okay? And that I have already chosen at the beginning. M naught and N naught, because they are orthogonal to each other. Okay, if they are not orthogonal, you can orthogonalize them. What is the procedure known as? Gram-Smith orthogonalization procedure. Okay, great. Okay, you can make them linearly independent, okay, and they will diagonalize that very matrix. Clear? Samajh hai? Okay, so let me give you an idea of such kind of matrices. Okay, so have what is this matrix called? It's a matrix, well-known matrix. Poly spin matrix, sigma x component. Okay. So how you diagonalize it? What are the vectors which will give the diagonal? This diagonal. Okay. So it is the linear combination of anybody. Okay, so these are the vectors. So let me write 1, 1. Okay, 1 by root of 2. 1 by root of 2. Okay, 1 minus 1. So you act the, okay, this matrix on this very vector, you will get actually 1 eigenvalue. Clear? Because this will give the eigenstates of sigma x operator. Clear? Okay, is it? How many values will be there? Plus minus 1. 2 values. Huh? So in other words, you can have this very matrix. Okay, so let's construct it. Then you construct it. Okay, so you are having this matrix at hand. Clear? Okay. So let's have this very objective. So now tell me what you are getting. So you're getting 1 by 2. So if you put a plus minus here, so you get plus minus here. So it will be plus minus here. Clear? So just check it. So is this now the eigenvalue equation? Is it an eigenvalue equation? First tell me, what are the eigenvalues? Plus minus 1. Do you see it? Okay, just it will be, because I have taken plus minus 1 out. Okay, so let's take, okay, first plus 1. Okay, so take the plus 1. Okay, is the eigenvalue plus 1? And if you take like this thing, 1 by root 2 minus 1 by root 2, so what you will get? Minus 1, 1 by root 2 minus 1 by root 2. Is it clear? So that means these are the two eigenstates which diagonalize this very matrix. How to do that? How to obtain that O matrix? Eh? So let's write that O matrix as, you put it in the form of columns like this, 1 by root 2, okay, 1 by root 2. This very vector, then 1 by root 2 minus 1 by root 2. So this is a matrix. Clear? Now take, so you call this as simply O inverse. Eh? So this we call as O inverse. Now take your O, this very matrix, so call this as some sigma x. Okay, sigma x, then you are having O inverse, what you'll get? You'll be getting 1, 0, 0, minus 1. Because what are the eigenvalues? Plus minus 1. Clear? This is how we construct it. Huh? Got it? In other words, I can say these two vectors, they are the good eigenvectors of this very matrix. Clear? समझ आओ? Got it? Okay? So, okay, now if you don't have actually, since here in this very example I have construct, okay, so first let me take the limiting case, then I'll comment on this very equation. Okay, so let's take the limiting case. Okay, let's assume this H11 or let's say there is no degeneracy. Let's say there exists only one state. So what is your state? K0 is equal to alpha M0 plus beta N0, is it? Let's take beta is equal to 0. What does that mean? You don't have N0. So let's take only there is only one of the possible states. Eh? So M0. So in that case, what will happen? Anybody? Which term will go to 0? So this term will go to 0. H11 minus H22, this will be 0. Clear? Is that true? Because it will be same thing. Huh? Okay, I am taking two independent states now. Is that true? Huh? Yes, this will become 0. And this will be a non-zero term. What you will be having ultimately? So E plus minus, that will be simply equal to H11 plus minus, okay, this mod of H12. Clear? So because this is the perturbation which will lift it. This is yesterday is that two-state problem. So this will simply lift up the energy. This will, okay. So there will be the energy splitting, like this thing. Clear? Okay, so let's put this beta equal to 0 in this very equation. Just put beta equal to 0. What you will get? You will get only one of the equations. Eh? Clear? So you will be getting this kind of situation, E plus minus. Okay, if you are not able to understand it from here, Okay, just put beta equal to 0 in this very equation. So what you are having only? Alpha and 0. Okay? So forget about alpha, put alpha equal to 1. So you are having 1 and 0. So what is the equation? Then H11, okay, that's equal to E1. Okay, clear? So the first order correction is how much? Okay, so let me not write this. So what is first order correction? E11. What is that? What is H11? So it is M naught, H1, M naught. Is this the first order correction to the unperturbed state? Is that true? So what will be then your this E, okay? So it will be simply E naught plus E lambda E. Clear? So now if you put alpha equal, okay, so this is for the case beta equal to 0. Now put alpha equal to 0. What you will get? So let's put alpha equal to 0 and put beta equal to 1. Because you are having beta and beta same. What you will get? Just tell me. So you will get the other way around, right? You will get E1 is equal to H2. Clear? So that means you are getting the correct perturbed energy at the first order level. Okay? Have you got it? Okay. Okay. Yes. So okay. So let's say assume in this very equation I don't know what are the good these eigenstates. Clear? I don't know how to construct them. Okay. So if I don't have any kind of information, how to construct them? Okay. So there is a very important theorem, although that's a very small theorem. Okay. That gives us actually that helps us to construct such kind of eigenstates. Okay? You got my point? Okay, so what is our question? First you should understand the question. Right? So what is our question? Then I will take the examples. Huh? Okay. So what is our question? Okay, so if I don't know a priori what are the good eigenstates that will diagonalize my perturbation matrix. Call this as a perturbation matrix. Clear? Okay, how to construct them? Okay? So anybody having an idea? You say loudly. No, suppose if I don't know a priori, I mean if I don't have any information, how to construct? How you are constructing that? Okay, I know in your this matrix algebra you are choosing a given basis, is it? And in that basis you are diagonalizing the matrix, clear? So how to choose that very basis? So you are having a physical problem here, is it? So how to choose that basis? Okay? How to do that? So I had to look actually the symmetry of the problem. Okay? Okay, so let me tell you this way. Forget about perturbation, everything let's forget about. Suppose if you have to construct the eigenstates of the harmonic oscillator. Okay? Clear? So it is actually you are diagonalizing the Hamiltonian. Hamiltonian is a matrix now for you people. Okay? We say when you are having a Hamiltonian, you say it is a matrix now. Clear? So you need to figure out the eigen values, okay, or the eigen energies of the harmonic oscillator for a given matrix. Clear? Okay? I will give a Hamiltonian for the harmonic oscillator, and I want you to figure out what? The eigenvalues, clear? Or the eigenenergies. How you do that? You diagonalize that very matrix. How you diagonalize it? You choose a basis set. Okay? From a given basis, okay, the way you are having here the basis, in this case, you are having two state vectors, clear? They form a basis in two-dimensional space, clear? Samashivan? Okay, so you have chosen that basis and diagonalize that very matrix. But for harmonic oscillator, how we choose that basis? So there is a kind of symmetry for the harmonic oscillator. Okay? So you define actually a number operator. Okay? You define the number operator and label your eigenstates, or you figure out what are the eigenstates of that number operator. Because the harmonic oscillator Hamiltonian and the number operator they commute. Is that true? When two operators commute, what do you mean by that? You can diagonalize them simultaneously. You can choose the eigenstates of one operator to diagonalize the other operator. Clear? Okay, so this way. So suppose if you are having, let's say, a number operator, and this commutes with the Hamiltonian of the harmonic oscillator. Clear? So this is equal to 0. This I don't know what is the basis set which will diagonalize this thing. Okay? But I know, let's say, if I know the eigenstates of this very number operator. Okay? Since this commutation means, okay, so vanishing of this commutation means I can choose the basis set of this very operator to diagonalize this Hamiltonian operator. That's why you are having, so this turns out to be very simple objective like this thing, n plus half. Clear? Clear? Got it? So you figure out the eigenstates of this very Hamiltonian as the eigenstates of this number operator. And if you write it in the diagonal form, so it's like this thing. So you are having h cross omega by 2, then 3h cross omega by 2, and so on. Clear? And what are the eigenstates? So the eigenstates are this 0 vector, 1, 2, and so on. Clear? So these are the eigenstates of this very number operator, and they are also the eigenstates of this h operator because of this very relation. Clear? So in other words, if I need to figure out, let's say, the procedure for diagonalizing this very matrix, what I require then? I need an operator which will commute with what? This h1, and that, in other words, that should commute with our total Hamiltonian. Okay? If it commutes with the total Hamiltonian, that means I can diagonalize this perturbation matrix in the using the eigenbase of that operator. Clear? Like we have in the case of harmonic oscillator. Okay? Got it? Okay, so let's do that. So okay, so let's take omega to be an operator such that, so you are having this omega, okay, h naught, this is equal to 0, and omega h1, that's equal to 0. So this does not mean I can simultaneously diagonalize h naught and h1. Okay? So it means only I can simultaneously diagonalize omega and h naught and omega and h1. Clear? Okay? So what is our problem? I need to diagonalize only with the h1, that h1 matrix. Clear? Okay. Let's say we are having two states. Let's write, okay, also. Okay, so the eigenstates of this are non-degenerate. Okay, so what does that mean? So let me take two states. Let's write some n naught. Okay, so let's write omega acting on this one. It gives you like m naught and omega with two distinct eigenvalues. Clear? So if such thing happens, so I am choosing n naught and m naught. Okay, these are the degenerate eigenstates of h naught. Okay, but they have distinct eigenvalues omega 1 and omega 2 for this operator omega. Clear? Here omega 1 is not equal to omega. Then I am having this h I j, this is equal to 0. Okay? So all the off diagonal terms go. Clear? So in other words, you can diagonalize it. Okay? Got it? Okay, so let's do it. It is very simple thing. Okay, so let's take this very objective. So what I am having by construction omega h1, that's equal to 0. Clear? So I can write this thing as m naught. So to be a Hermitian operator, it should be a Hermitian operator. It is a must. It's a must. It has to be a Hermitian operator. Okay, like this thing, h1 minus h1 omega. Okay, acting on n naught. This is equal to 0. Clear? You put n naught on this side and m naught on this side. Take this overlap. Okay. And now, since this is a Hermitian operator omega, that's why you require actually it as a Hermitian operator, so that it will act both right way and the left way in the same fashion. If it is a non-Hermitian, on the right it will act on one way, and on left it will give actually the Hermitian conjugate. Clear? It will give a complex. So the number will be simply complex in general. So when this omega will act m naught, what it will give me? Omega 1. When this will act on n naught, you will get omega 2. So it will be simply like this thing, m naught h1, and that's equal to 0. So by construction, omega 1 is not equal to omega 2. Okay, since omega 1 is not equal to omega 2, which implies this m naught h1 n naught, that's equal to 0. So, or in other words, since m and n they are not same, okay, so which implies hij is equal to 0 for I not equal to g. What does that mean? So it means the off diagonal terms go up. Clear? So from the eigenstates of that omega. Clear? Now once off diagonal terms go, what remains? On that means you are having a diagonal terms, a diagonal matrix. Clear? Okay. So this is the proof. Simple proof. Okay. So let's take the example. Okay. So let's first write what is our So, any question till now? So let's try what is the method of degenerate perturbation? Okay. So let's write it. What is the method? So what you need to first identify. Okay. So now let's say I am giving a problem. For the degenerate perturbation, how you will do it, how you will start with it, in general, how to do it. Okay, so we will only be doing up to the first order correction of the energy. We will not go to the second order correction. That's a little bit difficult in case of degenerate perturbation. Okay, for you people, you only require the first order. Okay, so first what you need to do, let's go step by step. What is the first step? Identify perturbation matrix. Clear? That's actually a G cross G matrix. Okay, for G-fold degeneration. Clear? Okay. What is the second point? Now tell me what is the second point? What is the second point? Okay, good. Second point is diagonalize. Okay, so let's call this perturbation matrix Hij. Okay, diagonalize Hij using secular equation as usual. So once you get these things, okay. So once you diagonalize, what you need to identify roots. Identify roots of the secular equation. Clear? So once you figured out the roots of the secular equation, what does that give you? The first order correction to the energy. Clear? For each level. Huh? So let's say if you are in two levels, you will get it. Both the levels will get split up. Huh? One will be lower in energy, another will be higher in energy. Clear? Okay. So identify the roots of secular equation with first order energy shifts. Clear? Okay, so here the point is the basis gets their the basis, I should say, gets are states that diagonalize. Since we need to identify what are the good eigenstates, okay, that will diagonalize this very thing. That diagonalize the Hij, the perturbation matrix, okay, or the corrected zeroth order correction. zeroth order gets states. I will write what to which whatever states go into for lambda tends to 0. Okay? Everybody got it? Huh? So you need to identify what so corresponding to each eigenvalue you will be having what? A state vector, okay? A good state vector. Okay, so let's take the example first, then you will identify what exactly it means. Samajh aa? So let's take the example. So this is the general way of doing the perturbation theory. So this is the example I have taken from Griffiths. Okay, it's a nice example. So let's consider a three-dimensional well. Yes. So let's take example. Let's consider a 3D well. Okay, infinite cubical well. Infinite potential well. Okay. So what is the potential? So you are having V, X, Y, Z. So that's equal to infinity and equal to 0. So let's say the well is like this. A 0 less. Okay, Y less than B less than C, and this is otherwise. Okay, so this is your well, a three-dimensional well, X, Y, up to Z. So it is X, Y, and Z. Okay, so this is your 3D well. I'm not good at drawing. Okay. Clear? So this is your A, this is your B, and this is your C. Okay? So the potential inside this very well is 0. Okay, it's simply the generalization of one-dimensional well. Okay? So what are the stationary eigenstates or the unperturbed states? So let's take the unperturbed states. So these are Nx, Ny, Nz. Okay, so let me put a 0 here. It means these are the unperturbed. So you solve this very well. What are the states? Okay, so you can decompose. Okay, so if you have not done this problem before, so how you do it? So you decompose it into 3 one-dimensional wells. Okay, for each one-dimensional well, the sign of x is a eigenfunction. Clear? Okay, so yes. Okay, so what you will be having? So you will be having 2 cube, rather like this thing. 2 by, okay, so let's consider it as identical well. So let's consider all the sides are same. Let's consider all the sides are same, because I am considering a cubical well. Okay, it will be simply 2 by A, 3 by 2. Okay, sine of nx pi by A x. Then you are having sine of ny pi by A y. Okay, then you are having sine of nz pi by A z. Okay, so these are the unperturbed eigenstates. What are the eigenenergies? So eigenenergies, let me write. So they depend on nx and y. These are the quantum numbers here. Okay, so 0. So what is that? Anybody? Pi square h square divided by twice m a square. Okay, so it will be like this thing: nx square plus ny square plus nz square. Okay, so now let's look at this very thing. So let's look at the ground state of this very problem. Okay, what is the ground state? Corresponding to the minimum energy, is it? So what is that?
1.
So because nx, okay, so what are the values of this nx? So nx, ny and nz, what are these values? They go from, okay, 1, 2 and so on. Clear? They do not start from 0, because 0 is a simple, trivial problem. It's trivially satisfied Schrodinger equation. So the values for this nx, ny, and nz, they are from where? 1, 2, 3. Why not -1? You can absorb the -1 into the normalization constant. Clear? Okay. So ground state will be simply equal to nx equal to 1, ny equal to 1 when all the values are same. Okay? So what is now the energy? So the ground state energy E11, so that is simply equal to 3 pi square extra square divided by 2s ma square. Okay, so now let's go. Okay, so that means there is no degeneracy for the ground state. Clear? Okay. So now let's take the first excited state. So what is the first excited state?
1, 1, 2.
So you need to consider now the combinations. The next possible combination, which will give the same energy. So let's put nx equal to 1, ny 2, and nz 2. Sorry, nz 1. Okay, or let's put this as 2, 1, 1. Clear? And then 1, 2, 1, and 1, 1, 2. Okay, so all will be having the same energy. Clear? Okay, so it will be like this thing: nx equal to 2, ny equal to 1, nz equal to 1. And then you are having this as 1, this equal to 2, this equal to 1, this equal to 1, this equal to 1, and this equal to 2. So what is the energy? So that means there are 3 states corresponding to the first excited state. There is a degeneracy for first excited state. Okay, so what is the energy? So let's write the first excited state energy. So Fs, let me put. So the unperturbed energy. How much is that? So it is 4, 6 by 2, it is 3 pi square extra square divided by m a square. So all these 3 states are having the same energy. Okay? Got it? Everybody followed it? Better samajha? Okay. So what are the states? Okay, so let's label these various states. So you are having states here 2, 1, 1. So you are having then 1, 2, 1, and then you are having what? 1, 1, 2. So these are the 3 states. I will label them like this way. Clear? Okay. So now let's calculate first the. Okay. So this is just we have not stated the problem. What is the perturbation? Clear? So let's state the problem. Okay. Okay. So let's add the perturbation. So add a constant perturbation like this thing. H1 is equal to sum 1 by 4, okay, V0. Okay, so V0 simply. For where I am putting this thing, if 0 a by 2, a by 2 or a by, okay, a by 2 is equal to 0 otherwise. What does that mean? Can you tell me what it means? So I am putting a constant potential shift. A constant potential I am putting in this box. Where A is equal to, okay, so this a by 2 and a by 2. Clear? And nothing about z axis. So it means I am putting this kind of potential here. This is the potential, some constant potential within this thing, this cubicle. Okay? So I am putting some potential there, a constant potential. Or in other words, you are just shifting the bottom by V0. Clear? So you are having a box, you put one edge of the box, okay, like this way, suppose. So this is your box, okay. So on this very side, you put it up, you bring it up. So the potential has now deformed. Clear? So this is the kind of perturbation what we are looking at. Now let's look at the its effect on the ground state first. What you will get? Okay, let's look physically. So what I am saying, I am having a ground state now. How the energy of the ground state will change? So what will be that? Since it's a constant potential, okay, it is simply a potential shift. Clear? So it will simply add the potential energy. Okay, it will simply add the amount of energy to the ground state. Clear? How much it will add? Say loudly.
You are adding a potential E naught, sir.
V naught, yes, V naught. Yeah.
That's V naught, sir.
How much? How much effect will be on the energy? So because it's only at where? A by 2 and A by 2. It's not the bottom. So you can think this kind of perturbation as well. You simply lift the bottom of the well up. Clear? So that will affect the V naught effect on the all the energies. Clear? So that will be simply the constant shift on the energy. But what I am doing here, somewhere within the certain portion, I am lifting the potential up. Clear? So how much shift will be there? Okay, so you calculate it. So let's calculate it. So on ground state. So let's calculate. So what is the first order correction? So it will be simply, what is the ground state? Let's call the ground state to be this one. 1, 1, 1. Clear? Okay. So it is simply 1, 1, 1. Okay, and there is H1, 1, 1, 1. Okay, so let's write it in terms of integrals. So what this is? Like, just tell me. It will be something. So why is the perturbation? Yes. Okay, so let's write first this thing. So you are having this in terms of the integral. Okay, so it will be simply, just tell me, it's a three-dimensional well, clear? So it is dx, dy, dz, clear? There is an integration over all the variables. What is this 1, 1? It is simply psi 1, 1, okay, star, clear? And then you are having this h1, and then you are having again psi 1, 1, okay? So x, y, z, x, y, z, clear? And I need to figure out what are the limits on the limits, clear? So much. Now which limit is restricted? Okay, what is h1? Okay, first let's write what is h1. It's v naught. Okay, so v naught, it's a number, it will come out. V naught. So let's write integral as such. Okay, integral over x, integral over y, integral over z. So what is this psi star? So let's take psi. What is your psi 1, 1? Put all n1, nx, nx, ny, nz to be 1. So it's 2 by a. So that will also come out. 2 by a. So it will come from 2 factors. So it will be simply 2 by a. Clear? Got it? Because half will go. Okay, so you will be having here sine of, okay, pi by ax. Okay, then you are having sine of pi by ay, and the other factor will come from here. It will be simply sine square. Okay, sine square pi by ay and sine square pi by az. Now figure out what are the limits of integration. Figure out the limits of integration. Huh? Figure out the limits of integration. Where is the perturbation non-zero? Just tell me. Since I am okay, so let me write this V naught here for you people. So look here. So you are having H1 is non-zero when 0 to a by 2. So this will go as 0 to a by 2. What will happen to y? 0 by a. What will happen to this thing? Simply 0 to a. Okay, because the box is of height how much? 0 to a, z axis. There is no change in the z coordinate. Clear? Okay, so V naught will come out. Now it is easier to solve because all the three functions are independent of each other. Clear? So you can solve them independently. Clear? Can you do it? So now how much is that? Anybody? So this is the first order correction to the energy. Okay? So you should not keep this. Huh? But you should not keep these things here. Okay? This way you will not learn. Okay? So now let's calculate the energy correction to the first excited state. Okay? So what are the possible states? So what I need to calculate? Tell me. Okay. So just tell me. So let's calculate this Hij. So correction, first order correction to first excited state. So what are the possible? What I need? These are degenerate. Clear? Yes, timer. So let's do it.